So this lecture is about designing asynchronous counters. So generally T flip-flops are used to design asynchronous counters. So let's understand the working of a T flip-flop. A T flip-flop has one input T which enables the counter, that is toggling nature of the T flip-flop, or disables the toggling nature of the T flip-flop. So let's assign 1 for that. T flip-flops require the clock for its working. So let's assume a positive edge triggered T flip-flop and two outputs, normal output and complementary output. Let's apply the clock frequency to the T flip-flop and analyze how the relationship between the input clock frequency and the output clock frequency. Now, so we will observe the output at the Q. Now let's draw the input clock, and since positive edge triggered T flip-flop is taken, let's mark the positive edges of the clock input. Now since the T is 1, for every positive edge of the clock, Q output complements, Q output toggles. This is the nature of a T flip-flop. So let's draw the output waveform. So this is the input clock and corresponding output we'll write it. So output assumed 0. So for the positive edge clock, it complements, toggles. Again for another positive edge, it complements, toggles. For every positive edge, it keeps toggling it. So this is the relationship between the input and output. One strange feature you can observe here, relationship between the input output. For every 2 clock pulses, 1 output clock pulse is produced. That means that we can write that output frequency is nothing but input frequency divided by 2. So this counter acts like a divide by 2 block or divide by 2 counting. So it has got a 2 state 0 and 1, and whatever the frequency will give it, output will be half of that. If I give 1 kilohertz, output will be 500 hertz. Now let's take now 2 flip-flop and just combine them, see the relationship between the input frequency and the output frequency. Now, so we are drawing 2 flip-flops and see that what is the relationship. Now, so T of both the flip-flops, T of both the flip-flops will be 1. So now input frequency will be fed to the first flip-flop, clock input. Now output of the first flip-flop, let's call as F1, the frequency, and that will be fed to the clock input of the second flip-flop. So let's mark F2 as the output frequency of the second flip-flop. Now, so we know that F2 is nothing but F1, which is the input for the second flip-flop, divided by 2, because every flip-flop divides the input frequency by 2, substituting F1 for the input clock frequency. So clock input, it is divided by 2 into 2. That means that it becomes a, so clock input frequency, it is divided by 4. So if I connect n flip-flops one after the other in this fashion, so we can say that output frequency of the last flip-flop, equals input frequency divided by 2 to the power of n, where n is the number of flip-flops used in the arrangement. So it can be used as clock divider also. This is the relationship between output frequency and the input frequency. If we have 2 counters of different capability of division. For example, so this, let's say this act like a mod m counter divided by m counter. That means that whatever the input frequency we give it here, it divides by m and given output frequency. And we have another counter which is act like a division by n mod n counter, and this is used as an input for this counter mod n counter, and this will be the output frequency. So if this is the input frequency and if this is output frequency and they have cascaded two of them, then output frequency is always given by input frequency divided by m into n. So this is the formula we use it to find out output frequency when two counters are combined and each will have a different mod value. Now let's start designing about asynchronous counter. Let's design the mod 8 asynchronous counter. Let's see the arrangement required for designing that one. So now, so this is the circuit diagram. What is required to design the mod 8 asynchronous counter? So 3 flip-flops are required because 2 to the power of 3 is equal to 8. So 2 flip-flops is not possible. 4 is more. So 3 is correct. So that we have used the 3 flip-flops. All are used as a edge triggered positive flip-flops. So I'll configure them as edge triggered. Instead of falling edge, we'll take the first case as a positive edge triggered flip-flops. Now, so what is the way the flip-flops are connected one to another one? The input clock frequency is given to the first flip-flop clock input. The Q0 normal output of the first flip-flop is connected to the input clock of the second flip-flop. Normal output Q1 is connected to the clock of the third flip-flop. So normal outputs are used in this connection. So the Q outputs of all the 3 flip-flops will contribute the output of the counter. Now let's observe that how does a counter works and what is the behavior. So count enable is nothing but shortening of all the T inputs of all the flip-flops in the counter and controlling them. If the count enable is 1, that means the counter works. If this is 0, counter do not work. It stops. Whatever the value it has got, it will just continue to hold the same thing. Now let's learn how this counter works. I'll apply the clock pulses now. So as we apply the clock pulses, it starts with a 7. So 1 1 1 is 7. Then 6, 5, 4, 3, 2, 1, then 0, then again starts with a 7. That means that the counting sequence is down counter. Started with a 7, reaches the 0, 7, 6, 5, 4, 3, 2, 1, 0, and then repeats. So this is how the down counters using edge triggered positive triggered flip-flops with this connection can be arranged. Let's draw the waveforms for this counter. So when we draw the waveforms, the principle what we use to draw the waveform is, so we have to observe the edge of the flip-flop, what is we have used it now. So the edge what we have used in this arrangement is positive edge because we have used a positive edge triggered flip-flops. So positive edges on all the clock inputs are marked. Since the sequence started with a 7 and reached 0, 8 different states are there in this counter. Mod 8 means 8 different states. That's why 8 clocks I have taken. Now, so for every clock input, the Q0 toggles. So you can see that Q0 is toggling for every positive edge of the clock input. Now, since Q0 is fed as an input to the second flip-flop, Q1 toggles whenever there is a positive edge happens on the Q0 signal. So that we can observe that Q1 toggles with reference to Q1. Whenever there is an edge on the Q0, Q1 toggles, and this is the output. Similarly, since Q1 is fed as an input clock to the last flip-flop whose output is Q2, Q2 toggles whenever there is a positive edge in the Q1 input. So we can observe that. Now, how do you mark the outputs in the timing diagram. Since it's a positive edge triggered flip-flop, with reference to clock, with reference to every clock input, that is after every one clock pulse. So after every positive edge, note down what is the value on the outputs. After the first positive clock cycle or positive edge of the first clock cycle, so we have marked Q0 is 1, Q1 is 1, 1. Similarly, after the second clock cycle, that is second edge, so we have marked the values of the Q0, Q1, Q2. Like this, we have to mark on all the, for every clock cycle, we have to mark the outputs. So that is being documented here as a table. This is the counting sequence. So 8 states are there. It's called as a mod 8 counter. Now, so this is a down counter. Let's say I want to design an up counter. So what is the change required? So let's observe that working of that up counter now. Now, for an up counter, instead of using normal outputs, complementary outputs are used to drive the clock of the next flip-flop. See, instead of Q0, we have used Q0 bar. Q0 bar is connected here. So Q1 bar is connected here. Let's observe the outputs now. We'll give the clock pulses. So I'll start from the first clock, first state. 1, 2, 3, 4, 5, 6, 7, and 0. That means that, so the count sequence here is up counter. What is the change we have done? Instead of Q outputs, we have taken a complementary outputs to drive the input clock of the T flip-flops. How do you write the waveform in this case? There is a one concept is there when we give complementary outputs as a clock inputs. So let's draw that and analyze it. So let's draw the clock waveform. I will mark the positive edges. Now for the first flip-flop, Q0 will toggle for every positive edge of the clock. Now we'll also write down now the Q0 bar complementary out of the first flip-flop, which is nothing but inverse or complement value of Q0, opposite of Q0. So when Q0 is low, it's high. When Q0 is high, it will be low. So I have written Q0 bar. Now, notice the relationship between the edges of the Q0 and Q0 bar. Whenever there is a positive edge on the Q0 bar, it corresponds to the negative edge of the Q0. In the up counter now, instead of Q0, you have used Q0 bar to connect as a clock source for the subsequent flip-flop. So that means that the positive edge of the Q0 bar is used as a reference in the timing diagram. But the positive edge of the Q0 bar is same as negative edge. So this principle has been used in drawing the timing waveform. So let's go to the timing waveform, analyze. Now, so since Q0 bar, that is complementary outputs, are used to drive the clock inputs of the next flip-flops. So the outputs Q1, Q2 are drawn with reference to the negative edge. Actually, the negative edge corresponds to what? Positive edge of the complementary outputs, as we have demonstrated now. So that's how in the timing diagram there is a difference. So Q0 always with reference to clock it is done. Since it's a positive edge triggered flip-flops are used, Q0 gets toggled for every positive edge of the clock. Now since Q0 bar is used to drive the Q1, Q1 gets complemented or toggled for the positive edge of the, sorry, instead of positive edge, negative edge of the Q0. So you can see that for negative edge, it has been toggled. Similarly, Q1 bar used as an input to the flip-flop whose output is Q2. So whenever the negative edge of the Q1 happens, the Q2 changes. Now similarly, so the outputs are documented for every positive edge of the clock and it's been documented in the table here. So it's an up counter. In the normal up counter, instead of normal outputs, Q0 bar, Q1 bar are used to drive the clock of the next flip-flops. Now, let's understand, instead of positive edge triggered flip-flops, if I use negative edge triggered flip-flop, how does the sequence changes? So let's take the first flip-flop where we use a Q0 outputs. So we know that. So here it was a down counter. Now I will configure every flip-flop as falling edge now. So I change this to the falling edge and this to the falling edge. Now, so now let's give the clock pulse. Earlier it's a down counter. Now we have changed the positive edge to negative edge. So 1, 2, 3, 4, 5, 6, 7, 0. That means that the moment I have changed positive edge to negative edge flip-flops, the down counter has become an up counter. Same way. So if I take the up counter with a positive edge, if I change the edge here, that is up counter becomes a down counter. So this is the difference we have to notice when we use different edge triggered flip-flops. Let's observe the waveform for the same thing. Now, so I have used here negative edge triggered flip-flops and Q0 outputs are used. So it's an up counter in a negative edge triggered flip-flop. How to draw the waveforms? Whenever we use a negative edge triggered flip-flops, instead of marking the edge, positive edge, you mark on the negative edges. Now Q0 complements for every negative edge because flip-flop is a negative edge triggered. So you can see that. So Q1 gets toggled for the negative edge. So we are using here the negative edges for changing the outputs. Again, where is a marking? After every negative edge, we have to mark what is the value on Q0, Q1, Q0. Same thing will be documented in the sequence. So this is what the relationship between output waveforms and the sequence with the edge of a triggered flip-flop. Now let's design a mod counter whose value is not equal to 2 to the power of n. In the sense, in case of mod 8, 2 to the power of 3 is equal to 8. That means the 3 flip-flops are sufficient and all the states are used. Now let's say we want to design the mod 6 counter. In a mod 6 counter, so what is required? We want to have the 6 states. So let's say mod 6 up counter. What is the sequence? Sequence is starting from 0, 1, 2, 3, 4, 5. So when it reaches a 5, it reaches a final value. Then it should roll back to a 0. That means that only 6 states to be used. How to design such a counter? So we have to do some mechanism. Once it reaches the last state, after the last state, the next state is 6. We don't want the 6. But 6 to be used as the way to start the first state. So what we do to identify the 6, we have designed a circuit. So we have taken an AND gate here. 6 is nothing but what? Q2 is 1, Q1 is 1, Q0 is 0. Wherever 1 is there, we have connected to the NAND gate input, same thing. Since Q0, it is 0 is there. So we have used an inverter. Now when the 6 comes, all the inputs of the NAND gate becomes 1, 1, 1 and it becomes 0. So I have to drive the counter to 0, 0. How do we drive? So we use an asynchronous input. So clear bar is an asynchronous input to all the flip-flops. They've all shorted together and connected to the output of the NAND gate. So after once it reaches 6, 6 will not be visible immediately. Within a very short time, 6 will be loaded into 0 state and then again it starts. So the same thing is shown in the waveforms here. You can see that the 5 is visible. The moment 6 comes for a very short time, you can see that a small glitch in the waveforms. Very short time, the 6 will remain and immediately driven to 0 state. This is how any mod value other than 2 to the power of n can be designed with the help of a gates which can clear the flip-flops. Now we'll see the working of that counter. So now here, since the clear was an active high here, instead of an AND gate, we have used here AND gate. And Whenever an inverter is required, we have used a bubble here. That means it's nothing but so inverter. So let's run this counter. Now it starts from a 1, 0, 1, 2, 3, 4, 5. 5 is the last state. After the 5, 6 will not be visible. Immediately driven to the 0 state. See that it becomes 0. Again start counting. So this is how you can decode any value and can able to realize any mod value. So if I want to design mod 4, I should decode for what? 4. If I want to design mod 7, I should decode for 7. In a similar way, we can design any mod counter with the help of negative edge triggered flip-flops also. If you use a negative edge triggered flip-flops, so instead of Q0 bar, we have to use Q0, we have to use it, and Q1 we have to use it to drive the clock of the next flip-flop. This is how it can be designed. So now, having understood the working of asynchronous counters, now let's find out what are the issues with these counters. So one of the challenge with these counters is the speed, the limitation of driving this asynchronous at high speeds. Why it cannot run at high speeds? Let's understand. Now let's take 3 flip-flops connected as mod 8 configuration. Now output of the first flip-flop is given as a input clock for the second one. Output of the third one, output of the second one is given as a clock input for the third one. Unless the output of the first flip-flop is produced, second flip-flop cannot produce the output. It has to wait, second flip-flop has to wait for the output of the first flip-flop to be generated. Similarly, unless the output of the second flip-flop is produced, the output for the third flip-flop cannot be produced. That means that if the propagation delay of the first flip-flop is TPD, propagation delay of the second flip-flop is TPD, and the propagation delay of the third flip-flop is TPD, then the total time required for the outputs to be visible on all the flip-flops simultaneously, it's equivalent to 3 into propagation delay of each flip-flop. In general, if we take the time for TPD for the first one 10 millisecond, so similarly for the 10 millisecond for the second one, 10 millisecond for the third one, total time required is 30 milliseconds. That means that total time required for the outputs to be observable at all the outputs simultaneously, it is a 30 milliseconds. To generalize this one, if there are n flip-flops are available in a counter, the total time or total propagation delay of the complete counter is n into TPD. N is the number of flip-flops, TPD is a propagation delay. Now, so let's find out the relationship between the input clock frequency and this propagation delay. Let's draw one clock waveform. Now, so this is the time period of the clock waveform. So T is the total time period of one clock. Now, after applying the clock input, the counter takes a propagation delay which is equivalent to TPD into N, where N is the number of flip-flops in the counter. So, before the next clock starts, second clock starts, the TPD into N should have finished. In the sense, all the outputs should be available before we apply the second clock. In the sense, this can happen only when TPD into N should be less than the T. So what is the rule? So T, that is the clock time period, is always should be greater than N into TPD. So then only the counter outputs are reliable. So that means in the worst case, TPD into N can be equal to T. That's all. TPD into N cannot be more than the T. So that's why. So there is a formula which calculates the highest frequency possible with asynchronous counter. It's equivalent to 1 divided by the period, 1 divided by the total delay of the counter, which is nothing but TPD into N. So this is a formula for calculating the highest frequency. Any frequencies higher than this, outputs are not reliable. So generally it's recommended that highest frequency should be less than this value. So even though it's an indicative highest frequency, always frequencies it can operate, it should be less than this value. So let's take an example. So assume that a counter is designed using a 5 flip-flops. So N is equal to 5 in our case. Assume the TPD is equal to 20 nanoseconds. Now, so the maximum frequency can be calculated using the above formula, 1 divided by 20 nanoseconds into 5. So substituting those values, 20 into 5, 100. Nanosecond is 10 to the power of minus 9. So bringing them to the numerator, 10 to the power of 6 into 1000, which is nothing but 10 to the power of 3. Denominator, substituting this value. So we get 10 megahertz. So this is the highest frequency. This is the safest frequency at which the counters can run for this specification. So this is one of the parameters to be taken when we design asynchronous counters. So in general, so we can always when we design a synchronous counter, always keep in mind propagation delay and speed limitation should be considered. And asynchronous counters are asynchronous in nature, in the sense because of the rippling effect, all the outputs are not produced simultaneously. So when you want to build a big circuit where a lot of uh, digital systems are there, all has to work synchronously. Asynchronous counters is not recommended because of the glitches in the outputs. And generally the natural counting sequence of asynchronous counters is binary, 0, 1, 2, 3, 4 or 4, 3, 2, 1 like that. If you want to design a counter with a different counting sequence like a BCD, the extra investment of the hardware and the speed consideration is a concern. So otherwise, advantage of asynchronous counters is very simple to design. No extra hardware is required. You just use Q or Q bar outputs to drive the subsequent flip-flops. So easy to design, less hardware is required. So to design asynchronous counters. So in the next video, we'll study about synchronous counters.